So our next talk will be presented by Mahidhar Tatineni on the experiences with MVAPICH2 and INAM on SDSC Systems. Mahidhar received his MS and PhD in aerospace engineering from UCLA. He currently leads the user services group at SDSC as a computational and data science research specialist manager. He has led the support of high-performance computing and data application software on several NSF and UC-funded HPC and AI supercomputers, including Voyager, Expanse, Comet, and Gordon at SDSC. His research interests are in HPC architecture and systems, performance and scalability, benchmarking, and HPC middleware. He has worked on many NSF-funded optimization and parallelization research projects such as MPI performance tuning frameworks, hybrid programming models, big data middleware, and application performance evaluation using next-generation communication mechanisms for emerging HPC systems. He is co-PI on the NSF-funded Expanse HPC system and the National Research Platform projects at SDSC. That's very exciting. So welcome, Mahidhar.
Thanks. Thanks. Can you hear me fine? Okay. So let me get started. So I'll talk about MVAPICH2 and INAM on our systems. So quick overview and then the outline there. Let me just start with the overview. So SDSC has been using MVAPICH on a lot of our systems. I mean, we operate and manage software on several HPC and AI systems, and the user base is quite diverse and spans a lot of scientific domains. And MVAPICH2 and MVAPICH2 GDR have been kind of on our systems, quite a few systems over the past few decades. So Trestles, Gordon, Comet, Expanse in progression. We're also testing out mostly development from Dr. Panda's group, basically experimental systems like Voyager, which have custom processors for deep learning. That system is actually currently in a testbed phase, so it's a good place to try things out. And then I'll briefly talk about INAM on Comet. Comet used to be an NSF-funded, it was an NSF-funded computer which was in operation for quite some time as an NSF resource. Once it was retired, it's been used for custom projects at the Center for Weather Research at SIO. So I'll start off with MVAPICH2 and MVAPICH2 GDR and Expanse. So Expanse itself, it's 728, actually now a little bit more, it's 784, I think now, standard compute nodes. And we have 56 GPU nodes now. This was the original configuration that's up there. And they're all InfiniBand connected. And we have a 12 petabyte Lustre file system that's split up into projects and Scratch. And we've looked at a lot of different application areas on Expanse. The Expanse system basically is made of scalable compute units. We started out with 14 and now we have actually 17. 15 of them are managed through Slurm, and 2 extra path racks that are actually Kubernetes based. So over 100,000 cores, I think, let me see if I can get my. So yeah, over 100,000 compute cores and 200 plus V100 GPUs. We have a limited number of A100 GPUs as well. And as far as networking goes, within a rack, we have full bisection. So basically, there's a top of the rack switch with 40 ports, HDR 200 ports, which 60 of those we split, we split that into 60 100 gig that go down into 56 compute nodes and 4 GPU nodes in each rack. And then out of the rack is 10, 100, 200 gig connections. So it's a 3:1 oversubscription going between racks. So that's been our, it's the workhorse HPC system at SDSC. So that's the same thing there. The GPU node itself, the bulk of them are V100 GPU nodes. So we have 4 V100 GPUs, 380 gigs of RAM. That's the topology there. Basically, we have NVLink within the node, which is a little change from what we had on Comet, was just PCIe and two sockets. So there's a bit of performance improvement there. So just starting off with quick benchmark results. Basically, this is the bandwidth benchmark. You can see we are almost getting line right there, so I'll just skip over that. And OSU latency and bandwidth for the GPUs. As you can see, there's no real difference between going GPU 0 and 1, which are on the same socket, and going between GPU 0 and 2, which are on different sockets. This wasn't the case on our previous system, like Comet. You would actually see an increase in latency because you had to go over the QPI. In Expanse, same goes for the bandwidth. We get pretty good bandwidth internally. We've been kind of doing this all through with our systems. We actually limit the scale of the jobs that people can run because we are more focused on having supporting a wider group of users and actually having fast throughput of jobs. So the limit on Expanse is 4,096 cores, and so I just did a all-reduced test at the max possible size that users can use. And I'm comparing MVAPICH 237 and OpenMPI 413 here, and you can see MVAPICH doing pretty well there. And one thing to look at is the improvement over the years. So I think when we first started on Expanse, we started with MVAPICH 234 a few years ago, and that wasn't really optimized for the AMD specific hardware. And over the years, as we are going from 234 to 236 to 237, you can see the improvement as we go along. And that's thanks to Dr. Panda's group, I guess. It's like the system gets better as we go along with new software. So, and MVAPICH is used to backend a lot of our installed software that our users run on Expanse. So some of the packages that use MVAPICH, and this, so on Expanse, we've kind of made no default MPI version because we found that some codes run better with our one flavor of MPI than others. But MVAPICH is used in a lot of applications, so XML, QChem, which some of these are commercial codes like QChem and Amber and LAMPS and NAMD. So you see a lot of molecular dynamics, quantum chemistry kind of codes. And at the bottom, I have both TensorFlow and PyTorch with Horovod, and I'll have some results for that today. So Neuron is one of the neuroscience codes that we run, and this is just showing the scalability going out to 2048 cores, and you get a little bit of actually superlinear speed up in the middle, but overall pretty good scaling for Neuron. And then this is the ResNet 50 benchmark with MVAPICH to GDR 237, so the latest version we have on Expanse. And with Horovod, and you can see it's pretty nice linear scaling on Expanse. And if you're wondering why I stopped at 40 GPUs, that's what I had free going up when I was testing. But I'm thinking this is going to be fine going out. Briefly on the AWP ODC, I think Yifeng had the talk earlier, so I won't go into too much detail, but you can see the impact of MVAPICH2 GDR with the CUDA versus non-CUDA aware performance, and you can see that both on the V100 nodes and the A100 nodes in this case. So that's Expanse, which is kind of our workhorse system with which all the users, like maybe over 10,000 users run on Expanse. So that's a bulk of our user base. But we have a lot of innovative systems, and Voyager is one of them. So let me go into that a little bit. So this is a category 2 system from the NSF. So this is meant as a test bed for innovative technologies, and you try out new kinds of processors and then transition them to production over once the test bed phase is done. So basically we have a 3-year test bed phase where we work closely with a limited set of projects and kind of optimize them and get their experience on these sort of systems. And then hope to get into the 2-year allocated phase after that, which will be a broader use kind of thing. So Voyager itself, basically it has 42 Intel Habana Gaudi training nodes. These Gaudi processors are custom processors for deep learning training kind of applications. And I'll talk about the processor itself in coming slides. And then we have 2 Goya inference nodes. These are the first generation Habana inference nodes. Again, these are specialized for inference. And we have 36 Intel x86 processor nodes, which are just for like pre-processing, managing data, that sort of stuff. All of those are basically in the system. Now, the Gaudi training processor actually has on-chip networking. So associated with that, there is a 400 gig interconnect switch that we basically use Rocky with, and basically that's the main network for the training processors. We also have a limited amount of storage deployed, and this is also flexible. Right now it's deployed as a Ceph file system, but we intend to kind of try different file systems and see what works well for this kind of workload. So a brief slide on the Gaudi training processor. Basically, it has 8 fully programmable tensor processing cores, about 32 gigabytes of HBM2 memory. And the main thing is the 100 gig Ethernet ports on chip, and it supports Rocky, so it's a pretty standardized setup for that, for the network side. So the way Voyager is set up, there's 3 different networks. There's the 400 gig network for scale out training, and I'll talk about a little bit at the configuration level. And then there are 6 connections from each Gaudi node to basically there is the non-blocking switch. And then we have a 25 gig bonded, so 2 25 gig network Ethernet cards on the host. So there's the on-chip networking, and then there's also the host networking. And the host networking is for basically file systems and the data path. And every node basically has this. And then there's a 1 gig connection for basically out-of-band management kind of stuff. So regarding the Gaudi chips themselves, so you saw that there were 10 connections, 10 100 gig connections on each chip, right? So each of the nodes has 8 Gaudi cards. So the way the network is set up, you have all-to-all between all the cards within a node. So 7 connections from each of those chips goes to the other 7 cards on the node. So that's full bisection, direct routing, all-to-all basically, right? So, and then you have 3 connections left from each chip. So that's 300 gig on each chip. So that's about basically 2.4 terabits of networking that is available to go scale out of a node. So what's been done is basically those 2.4 terabit it's basically there's a retiming setup so that you can do 6 400 gig connections out from each node. And those go into basically the Arista switch, which is a 400 gig switch. So that's kind of the training processor network essentially. So that's natively integrated Rocky on the processor. And so as I said, like you get 6 of these 400 gig connections out. So a lot of networking available for scaling out essentially. So that's the network side of it. So now the software stack, what Habana has done is actually try to make it as easy as possible for the end user to run on these systems. So what they've got is at the high level, they try to keep up with the latest PyTorch and TensorFlow frameworks. And so the end user is actually programming in TensorFlow and PyTorch as they usually do. There's basically a list of operators that they support within these frameworks, and it's pretty extensive and always being updated. They come out with an updated stack every couple of months actually, so it's quite rapidly developing, and they support a lot of standard models. So at the high level, the user a lot of times doesn't have to change the code much. There's a little bit of a tweak on which version of TensorFlow you load and so on. The Habana has its own custom version. So as long as you load those, you're pretty much not changing your code much. And even on the scale out, they have tried to keep to the standard kind of framework. So they support Horoward for TensorFlow and distributed options for PyTorch, which are very standard, so that the people who are used to scaling out these machine learning frameworks can actually keep most of their code unchanged. But they do have underlying like a communication library, and they actually have options to develop custom kernels and so on. So I think as Dr. Panda's group sees that, they were like, oh, we can write MVAPICH on this because if that's exposed, we can do that. One brief thing before I go to the MVAPICH aspect of it is that all of this we run through Kubernetes on Voyager. And the entire software stack, like the Synapse AI software stack, is in a container. And Habana always updates these performant containers with the latest Synapse AI stack that they have. And they're available publicly on their vault. So you can just pull directly from their vault when you're running in your container, in your Kubernetes setup. So Voyager itself, so basically, the way we've set it up is to run through Kubernetes, right? So Dr. Panda's group, Chen Chen, I think, yes, I don't know if he's here. So basically, they provided us, so within Kubernetes pod, you can basically mount a directory at any location you want. So the way we decided to do this is to actually mount it in user local apps and install it into a directory there. And then it ends up on a host path underlying, right? Because that's what's mounted. And then from an end user perspective, when they launch the Kubernetes pod, they just need to mount it in the right location, and then you pretty much have it there. Now, we could also do another thing. We could stick it in the container and just create another container, just layer it into the container, which is what we'll end up doing, I think. So just make it easier. But right now, this is how we're doing it. And it's easy to use in that sense. So as I mentioned, we use Kubernetes. So the specs are usually done using YAML files. So this is an example YAML file. I don't know if this is readable, but basically there is a location on host which we can pull into the pod. So you basically give the location on the host. This is a container which has the Synapse AI stack, And this is where we tell the mount location within the pod. And that's pretty much it. And after that, it's like you run MPI run RSH with all the flags that you want, and it runs using the MVAPICH2 that was developed with the backend to the Habana setup. So from a usability standpoint, it was actually pretty easy. I think it took me maybe like 20 minutes once Chenchun provided me the location. It was easy to kind of set that up. So this is early days right now. I think Chenchun had results on in his talk, so I won't go into that detail. But I mean, the goal is, since in the I think Dr. Panda mentioned it yesterday. The goal is, like, if we can develop kernels using their API, then I mean, technically we can run non-deep learning things on the chip, or something that is more customized version of the algorithm if you want to kind of. So you can play around a little bit, and it's ongoing work, and we are hoping we can get more access to the lower layer of even the communication libraries, so that the MVAPICH could be tuned better too, right? So there's a lot of opportunity there, so stay tuned. Hopefully we'll get more nice results out of there. So the last thing I want to talk about is INAM on Comet. So if you've been coming to MUG earlier, you probably have heard me talk about Comet before, but basically it was an NSF-funded supercomputer which preceded Expanse and had Intel Haswell processors. Once it was retired from NSF use, basically the Center for Western Weather and Water Extremes, CW3E, took it over to basically run it for their climate simulations and weather simulations. So the bulk of the use is for actually ensemble simulations during the wet season in California. So they try to predict the precipitation rates and storms in California. So that's their goal. And they run a lot of ensemble simulations every night to basically get near real-time forecasts. And if you go to their website, you can see the cool forecasts that they put out every day. I think the next season's going to start very soon, like September or some mid-September, I think. So we'll start seeing those runs again. We are still managing it, and there's a bunch of compute time on that. So just a quick look at the network architecture for for Comet. So it basically had 72 nodes in a rack, and the switching was basically 18 nodes to a switch, and then you had four switches within a rack, and then layered into 3 switches, and then going into the core fabric. So that kind of is the setup. So why did we want to do INAM? So it turns out, like, and this, by the way, never happened when we were running this for NSF, but once CW3 workloads were put on, they had a slightly different workload, and some of the workloads were both I/O intensive. They have a lot of data flowing through Luster, and also communication intensive. And it actually, we found problems. We actually had congestion issues, and we were trying to find the source of the issue and kind of see if we can do something about it. So that was our original motivation to put INAM on that. I mean, we want to use it for network fabric health monitoring and kind of looking at utilization and so on. And then the goal is to also enable Luster traffic monitoring, so we can get a handle on the I/O aspect of their workloads. And then use the MPI information to kind of evaluate the impact. So the experience, so thanks to the folks at OSU, basically we got a custom INAM RPM for Comet and the particular OFED stack. I think pretty minor issues setting it up. We had, I think, an issue parsing a switch map file, which worked okay once we got rid of some blank lines, I think. And right now we have it set up for internal use. I think we might need some user auth kind of setup to enable end users to look at it. But right now the use is mostly from the admin side for us to kind of figure out what's going on, so this part is fine. There was some initial slowness for Phantom.js to pick up the cache info, but once that was there, it's pretty quick, like it's less than a second to kind of respond, so it's pretty nice. And we looked at all this and said, hey, we can do this on Expanse too. So that's coming up next. We'll basically evaluate the use of ClickHouseDB as a backend in that case. On Comet, it's set up with MySQL right now. So that's the full system network view from INAM of Comet. Looks very busy, but actually you can see the patterns. So like if you look at a block here, that's essentially one rack, and if I zoom it in, you can see, remember I talked about 4 switches in a rack, so those are the 4 switches, and you can see the 18 nodes in each part there, and those go into the 3 next tier of switches, and then that goes into the core director switch. So it's kind of nice, and you can zoom in a little bit more, and you can go down to the level of a node and look at things, of course. So that all works nice. We've also set it up for notifications. If you look down here, I don't know if it's visible, but we set it up to actually see if a link utilization goes above 95%, and also if there are problems, of course. And just yesterday, both happened. So there was this one link that went above 95%, and coincidentally, that was the Lustre OSS. Our Lustre file system is in the Fabric. So basically, that's OSS 1.5, so someone must have been pushing quite a lot of data into that OSS, and that maxed out the link, basically, almost. So that's a good part, and then we also found a problem link on one of the nodes, and I think that was a node that probably got rebooted. But basically, you can actually see, if you click on that, you get additional info on which particular link it is and between which host or host and switch and so on. So this is useful, actually, for us to kind of automatically get a trigger and catch problems, and so we'll stick it on Expanse also. You can get job level info from INAM as well. So this is 2 different jobs, and you can basically query it by job ID. It's integrated with Slum. So basically that was a nice thing. This, I think, will be useful again if we see some performance issues with a job. We can probably go back and look at things. So overall, pretty nice information from all of them. So so just to summarize, basically, on Expanse, we extensively use MVAPICH2 and MVAPICH2 GDR. On Voyager, it's a custom processor for AI, so it's in the test bed phase, and in the MVAPICH aspect is also in the testing kind of phase. So hopefully we'll get some good results out of that. And you just saw the INAM on Comet. We'll extend that to Expanse. One other thing, I didn't mention this new system at all. Probably next mug, this is what I'm going to talk about. But we have the prototype national research platform, which is a Kubernetes-based system that's distributed across the country. But at SDSC, there's an HPC component of that that has FP64 optimized GPUs. These are A100 GPUs, except they're on a composable fabric. So we have GigIO hardware in the system. And these A100 GPUs are actually disaggregated in APA boxes. So technically, we can compose them to any node in that system that has the PCIe backend for that. So as you can imagine, there'll be MPI associated with that, especially if we stick 16 of them in one GPU, one node, and we have to do that. So we're going to need some help there, I'm sure. So they do have a libfabric setup, GigIO, so I'm hoping it's not too hard to use that with the MVAPICH2. And separately, we have FPGAs that are also on the composable fabric. And I think someone here is already working on on the MVAPICH for that. So coming soon, I guess. With that, I'll stop.
Do you have any questions?
Yeah, I'm interested in, thank you for the talk. Interested in the Voyager, where you have the special whatever, what's that name? I forgot.
The Gaudi processor?
Yeah, the Gaudi.
Yeah.
So it sounds like that's built on tensor processing, right?
Yeah.
So it's, in a sense, direct competitors against the TensorFlow TPU from Google?
Well, I guess that and I guess GPUs from...
Okay, because Intel does have a GPU thing come out.
Yes, they have them too. And I think if you look at the roadmap, they might be mixing the two. Like,
so one is for tensor computing, the other one is for what?
no, they might actually merge the
two different
kinds
designs.
of approaches, because the on-chip networking is the big part of this, I think.
Okay,
that
so
might
they
be
are
coming.
experiencing
Yeah.
with this. So this, if I understand the one correctly, so one simple chip has what, 16 tensor processing unit on
8, I
that?
think. 8 tensor processing on
8
each chip.
unit.
Yeah.
Then all those 8 units on a single chip is connected through Ethernet.
Correct, yeah. Roughly.
Okay. Now, one problem with Ethernet used to be it's a startup.
The
It's high.
latency, right? Yeah.
Okay. Does it play any role here?
I think the rocky part probably helps a little bit, right? Like to lower the latencies. I think, I don't know, if, Amit, you want to say something?
Rocky does help quite a bit,
Yeah,
but still
but it's
Rocky
still-
is higher than IB.
Yeah, then IB for sure.
Yeah, at least twice.
Yeah.
So that does not pay any penalty here?
I think it's probably going to be like 2 or 3 microseconds, right? Like between 2 and 3 microseconds. Yeah.
No, every message you send, there is a
But
startup.
usually the deep learning, the message sizes are large, right?
Okay.
So usually
So that may not be matter
Yeah.
too much. But the thing is, I don't see you have any memory attached to that. Does it?
there's HBM2 on the chip.
There
There's
is.
32 gigabytes of HBM2 on
So
each chip.
that is directly attached to each of the chip?
Yeah,
Okay. Now,
within the chip, yeah.
then all the cores, a so-called processing unit,
Yeah.
share that
Yeah,
memory.
they share that. And
And it's coherent across that,
it's coherent across that, yeah.
through that on-chip network. Okay.
Yeah, yeah, I had a question there. That pretty much scales pretty linearly all the way out, like.
That reminds me of another thing. You said you don't need a significant programming change. Do you say that it's compared to CPU style programming or
No, I'm
compared to
talking about
GPU type?
GPU. Like I'm talking about if someone already has like a GPU set up for within PyTorch or TensorFlow,
Okay.
translating that to Gaudi is a lot
Gaudi
easier.
is,
Like, it's
you
very
have a-
minor
okay,
changes. I mean, the only caveat I have is it's not fully supporting all the operators, so that's the only thing we have to check.
Okay.
But things like large language models and NLP,
But
it's
then
pretty
does it matter what unit you download to that? How much of a computation you download to that?
yeah, I mean, I don't know if so this is the first generation processor.
Okay.
I'm not sure what the memory is on the second generation. Did it go to 80 gigs? I don't remember. Like, yeah, I think it might be 80 gigs.
Okay.
And they're about to come out with the third generation, I think. So things are going to improve, I think. Yeah.
Yeah, very nice talk. So I had a question that when you showed the when you showed the new processors schematic, I saw that there was a GEMM kernel.
Yeah, there's a GEM engine also.
Yeah, so which means that if you have, say, like I'm thinking of the of basically scientific computing world, load. So say if I have a numerical method, which I actually have, but that uses like matrix multiplications a lot, then
Yeah, you can probably do something. Yeah.
we can, like if I put it in PyTorch or some sort of a Python-based language, then you could run it.
You can run it, yes.
Oh, I see.
Technically, I mean, there is a flexibility. It's just that the intention of the developers wasn't to use it for that kind of stuff.
Yeah, but like these days,
But they do have a API. They have a C API to their.
oh, even
thing.
C, have
Yeah,
even a
so-
C API? Okay.
Yeah, so we should technically be able to do a lot of things. I think that's what Dr. Pandava meant yesterday when he was saying, it's like you can do other
Yeah,
things.
yeah, because
Yeah.
nowadays you have these new like numerical
Yeah.
methods that do a lot of matrix, so like that do a lot of matrix,
Yeah,
like not just matrix anymore.
yeah, you should be able to do it. It's just that, their Habana's priority is on the deep learning
Yeah,
side
yeah,
and
that's where
pushing
the
towards
money,
that,
yeah,
right?
yeah,
So, but yeah, it's in a test bed phase, so we're going to play with it. It's going to happen.
Yeah. Okay. Okay.
Yeah.
Okay. Thank you.
I had a quick question.
Yeah,
May I please? So, yeah, I'm very happy to see the inclusion of FPGAs in the PNRP platform. So, was there any motivation or driver behind this early, adoption of FPGAs in the system, or is there any application-driven kind of motivation?
Oh, yeah, so originally in the proposal, we had, I think, 3 application areas we were thinking of. So molecular dynamics was one. The particle physics folks have a lot of work that, so they, like the experiments at CERN, they're getting a lot of data, and they subset them or do a lot of processing on the fly. So the FPGAs are really good for that sort of stuff. So they're actually already using these systems, the ones that are on NRP. And then third thing was some of the bioinformatics workloads have been put on FPGAs. So there's a group at UCSD, Dr. Diana Rosing's group. So they're working on those workflows. So those 3 were kind of what we had in mind. Once we put them out, I think there's a lot of networking people getting on there. So people find other users, right? So yeah.
We'll be happy to learn more about
Yeah, definitely. We can talk, yes. Yeah.
Sure. Okay.
Thanks.
So thanks very much. Let's thank our speaker. And we're back on time. Wow. So let's just open the speaker slides. So our next talk will be on accelerating HPC and deep learning applications using MVAPICH2 DPU, X-scale